will try to talk about the continuous charge distribution at a time, so that we can cover the two lecture in this same topic. So I'm not going to do basically that more than 2 or 3 problem in one live session, because we are also uploading some video from problem solving session actually, so you can also access that one. So let me allow to share my screen with you. So can you see my screen?
Yes, sir.
Yes, sir.
Fine. So the topic name is electric dipole moment is independent of the origin. This is the topics we are going to talk about today. So before that, we are going to introduce what is electric dipole moment. Electric dipole moment, or how do we define that one? Say if you keep 2 point charges, they have the same magnitude but in the opposite polarity. So you have a charge plus q over here, and another say that minus q. It has also the magnitude the q, but one is positive, another is the negative. And the distance between these 2 charges, say that from center to center, say that the d. Sometimes also we express by the r. Then the electric dipole moment, which is expressed by a vector, actually it has some direction. The electric dipole moment we express, it should be charge into r, where r is the distance between that 2 vector. So this one actually we have to write down in a form, because there will be a I equal to 1 to n. Say this will be the qi and ri, right? So this is actually the general form of electric dipole moment. So sometime, because we can express this, the magnitude of this electric dipole. So we express in your book, they express in that form. So P actually Q into D, where D is the distance between them. I write down, say this is actually the Q1 and Q2. Say if there is a 2 pair, 3 pair, or 4 pair of charges, then we can generalize that equation in that form. So this is be that general form of electric dipole moment. Since the electric dipole moment is a vector, it has some direction. That direction would be always from negative charge to the positive charge. So this is to be the direction of electric dipole moment P. So that's how actually we express that electric dipole moment. Say, let's introduce that dipole moment in different orientation and different scenario. Say I have a case like that. I'm going to choose. So this is my x-axis, and this is actually the y-axis level. So this is my x-axis and this is my y-axis. So I have 2 charts. So this is Q1, which is plus Q, and this is, say that Q2, which is minus Q. And then the distance, or you can say the coordinate of these 2, basically you can say 0, minus A, and say this is actually the 0 A. I choose this is actually origin. It means that this distance is basically that A, and this distance is also that A. Now say I want to represent by a vector that one. Say for simplicity I don't have to, but I am going to do that so that you can understand. So this distance is R1 from center of this origin, and say this distance is R2 from origin. Then electric dipole moment for this pair of charges, we can write P would be Q1 R1 plus Q2 R2. Right? Now I'm going to put the value of this Q1 is basically that plus Q, and R1 is that distance that I can express A into Z hat, right? Because I know that length from 0 to that Q1 position at a distance A. Fine. Now the minus the polarity of this charge actually, Q2 actually the minus Q into A, and this A is basically towards that negative Y direction. So that's why I use the unit vector minus J hat. Now I can write down this formula would be, or the electric dipole moment would be QA Z hat plus QA Z hat, which basically give that P would be plus twice QA Z hat. So that's mean the electric dipole moment will be basically 2AQ. We can write in also that form actually, the 2AQ into Z hat. 2A basically the distance between these two charges, right? That distance will be basically the 2A, and the direction of this dipole moment actually you can find out towards the positive Z hat. So towards the positive Z hat means it would be towards that direction, which is basically from negative charge to the positive charge. So that's why we can express that electric dipole moment in that form. Fine. Say this electric dipole is independent of origin. Independent of origin means if you shift your position, shift your origin, or shift the charge particle of this origin, the electric dipole moment is not going to change. Say for this case, we find out the electric dipole moment is this one. Say right now, I'm going to change the position of these charges. What would be that in that case, the electric dipole? Say I'm going to write, say this is actually, this is actually that Q2, which is basically the minus Q, and say this is actually the Q1, which will be that basically that plus Q. I keep the all other thing is basically that same. Then I can keep, say this is actually that corresponding distance would be that R2. This in that case, this distance would be basically that R1. Right, I just shift the position of the charges. First one, I say this is Q2 is negative, and now right now this is Q1, but this one is also the positive. I just shift that position of the charges. Then I have to find out what will be the electric dipole for this case. Fine, I can write that electric dipole moment would be Q1 R1 plus Q2 R2 is the general definition of the electric dipole. I'm writing in that form. Then this P, Q1 is plus Q, right? And this is the distance from center to that one. And that distance will be towards the negative Z hat, right? Now the Q2 is negative, or I should write down in that form. So Q2 is minus Q into A, and R2 basically towards the positive Y direction. That's why I write in that form. Now look at this. If you do that, this is would be P is a minus QA Z minus QA Z. So that will give me basically P would be minus twice A Q into Z. Or I can write this P in a twice A Q into minus Z, right? So this is actually the electric dipole. Minus J hat is basically indicating the direction of the electric dipole. So minus J hat means it should be towards, right now it would be towards that direction. But the magnitude are remains same, twice a Q. So that thing we also find out over here, twice a Q, but it was from the negative to the positive charge. Fine. What if, say, I'm going to choose that case right now, I'm shifting my origin. Say, let me copy this one. In that case, I don't have to draw that. Sorry. So I keep the charge in the same way, or I can shift the charges if you want. So I should shift the charges so that you can. Right now, say this one is positive. So Q1 is negative. Right. So, and say I choose the origin over here. So I'm going to calculate that electric dipole moment from that point. So in that case, say I'll say this is would be my R2 vector, and this one would be my R1 vector, position vector. Right. So this is my origin over here. Fine. Say let's write down. So this one I can write say this P would be Q1 R1 plus Q2 R2, right? Now this Q1 is minus Q into R1 plus Q into R2, right? Then P could be written as, I can factor out Q, it should be R2 minus R1. Now R2 minus R1 means, say this one is my R2, which is that vector, and this one my R1. If I write down this is the minus R, then I can draw it over here. So I'm going to use a different color. Say it should be this one, I can say this is actually the minus R1. I just shift that vector from here to here. There's a reason why I do that. Then look at this. This R1, R2 head is connected to the tail of the second vector R1. Then R2 plus, if I write down this R2 vector plus minus R1 vector using the vector triangle law, I'll find out R2 minus R1, and that vector would be from resultant vector would be towards that direction, right? Using the vector triangle law, we can write down this one. And if we do that, then we'll find out that this thing would be also that same. So P would be Q into R, and these are, look at this, from negative to the positive charge. So this is actually the direction of that dipole moment. So we find out the same thing. Now, if you could find out that value of R, in that case, we can also find out that electric dipole moment would be basically independent of that origin. That way, we can say that the electric dipole moment would be basically independent of origin. Fine. Say now I'm going to mathematically prove that one. Say that this is would be independent. So that's mean it will be the same in everywhere, right? So consider I'm going to choose a case. So there are two charts. All right, choose a different column. Say this is one charge is minus 10 microcoulomb. Another charge over here, this is plus 10 microcoulomb. So this is actually the center of this one. And I'm saying that this is actually that origin O, this is the point A, and say this is the point B. And distance between that two point A and B actually the 5 centimeter, not centimeter, it's a 5 millimeter, I'm sorry. Then I'm going to find out the dipole moment at origin O with respect to O. I'll find out the electric dipole moment with respect to point O, A, and B. Electric dipole moment at O origin. If I do that, then what I can write? So my P would be Q1 R1 plus Q2 R2, right? This is actually the equation. Now, what is R1? R1 would be the distance from origin to that charge. So this is actually that R1. I'm choosing, say this is actually that R2. Now, if I plug in, say Q1 is 10 microcoulomb, right? Which is, I'm choosing, say this is also the Q1, and say this is actually the Q2. So Q1 is plus 10 microcoulomb, 10 into 10 to the minus 6 into R1. So R1 would be the distance from center to that one. Since the distance between A and B actually the 5 millimeter, then from center O to B point would be the 2.5 millimeter, right? 2.5 into 10 to the minus 3. From millimeter, I convert to the meter. Into that direction would be I head from towards that direction. Now, what about the Q2? Q2 is basically minus 10 into 10 to the minus 6 into 2.5 10 to the minus 3 into minus I hat. Say I hat because I choose, say this is my positive x direction and say this is my positive y direction. Right. I'll find out this equation basically. So then what would be the case? I can write, this is will be, look at this, I can write, if you do that calculation, you are going to find out it would be 2.5 into 10 to the power minus 8 I hat if you multiply that one, and plus it will be also 2.5 into 10 to the minus 8 I hat. In that case, I'll find out the electric dipole moment, 5 into 10 to the minus 8 I hat coulomb meter. So that would be basically that electric dipole moment. Now we can find out that magnitude another way, the formula we give you, right? That shortcut formula, you can verify that one. Twice QA I hat. So 2 into QE is basically 10 into 10 to the minus 6 into A, which is actually 2.5 into 10 to the minus 3 I hat. If you do that, it will be also 5 into 10 to the minus 8 coulomb centimeter I hat, sorry, coulomb meter I hat. So that should be actually the electric dipole moment with respect to the origin A. Fine. Now I'm going to find out with respect to the point A. So that's mean if the origin, at A, I will choose the origin at point A. Let me allow to make a copy of this one. So if the origin is A, then what can I write? I can write, so again, my formula I'm going to use P actually Q1 R1 plus Q2 R2, right? So P would be at the point, say I'll write down the Q1 is this is my origin, right? With respect to that, this one I'm saying that distance is to be the 5 millimeter. So 10 into 10 to the power minus 6 into 5 into 10 to the power minus 3 I hat, right? This is the Q1 plus minus 10 into 10 to the power minus 6 into the distance from that point to the location of the Q2 is basically that 0, right? So that's why, and it should be say that unit vector you can write down and that from this, it is at the origin. So that's why we'll find out. So this is would be again 5 into 10 to the power minus 8 coulomb meter I hat. So towards that positive x direction, because this is would be basically the direction of that electric dipole moment. It should be from always negative to the positive charge direction. So this is would be exact direction of the electric dipole moment. What about, say, if I choose the origin at point B, if the origin at point B. The origin at point B, then what we can write, so I'll write in that case that P would be Q1 R1 plus Q2 R2, right? But this one would be basically that 0, because if I choose this is my origin, in that case with respect to that one, R1 will be the 0, right? So that's why you will find out the Q2 into R2, and Q2 is basically minus 10 into 10 to the minus 6, and the R2, so since I choose that origin over there, then the position vector will be towards the negative x direction. So that's why I can write it with that 5 into 10 to the minus 3 into minus I hat. In that case, I'll find out this minus is going to the plus 5 into 10 to the minus 8 coulomb meter into positive I hat, which means that the electric dipole moment is still remains same. So magnitude is 5 into 10 to the minus 8 coulomb meter, and the direction is towards the positive x direction. So that's when it will be towards that direction, the direction we shown by that color. So that's why we can say that the electric dipole moment is independent of that origin. You understand? Any question over here? All right, let's talk about, say, continuous charge distribution case. I have said that a scenario where is a infinite long charge of linear charge density rod, which is a charge density is 0.6 microcoulomb per meter, lie in the z-axis, shown is over here, and a point charge plus q, which is 8 microcoulomb in the y-axis at a distance y equal to 3 meter. Now they asked me to find out the electric field at the point P on the axis x and at x equal to 4 meter. This is actually, we have to deal with that point charge and continuous charge distribution at the same time, right? So look at this, that electric field by the contribution of this point charge, which is a plus, it would be towards that direction. So that's when it should be downward towards the YZ plane. And since a positive charge by the rod, that electric field contribution would be towards that direction. So that's why this is the electric field contribution by the L line of charge, and this is EP, stand for the electric field for the point charge contribution. Then we can say that the total electric field would be basically E net would be basically electric field contribution by that line charge plus electric field contribution by that point charge, right? So first I'm going to find out the electric field by this line charge distribution. Then I'm going to find out the electric field for the point charge distribution, right? The point charge is very straightforward, you can find out. To find out that electric field that by the line charge, we will define a parameter. It's called actually that linear charge density is lambda, actually charge per unit length, or differential charge divided by differential length is with the same. My idea is that what I'm going to do basically to find out that continuous charge distribution is that, say I have, this is a rod, and in this rod the charges are homogeneously distributed throughout the rod. Then if I take a differential element, say that this one which has a charge, say del q, and the length, say that del z, and the say total charge is q and total length is L. If I take, say the ratio total charge divided by total length, if I take the differential charge divided by differential length, if the quantity and the ratio are same, then we can say that this would be the linearly distribution of the charge. That's the definition of the linear or homogeneous distribution of the charge. Same idea we can use for linear mass density. This is a linear charge density parameter actually. We have also basically that we already known that if you go through that continuous charge distribution video lecture, which is lecture 4. So we have two-dimensional. It's called the surface charge density and also for the volume charge density. Right now we are considering 1D case actually, because this rod is infinite length with respect to that other side. So that's why we can neglect. This will be the one-dimensional case over here. Now the idea is, say that if I could find out the electric field for this Q charge at a distance, say that Z along to that direction, then to find out that whole rod contribution at that point, I'm going to just integrate that rod from, say that depends. I can choose, if I choose the origin over here, then I can integrate from minus L by 2 plus L by 2, or if I choose the origin over there, then I will integrate from 0 to L. Then total rod, the electric field at that point, we can find out by integrating that one. Right? So this is actually the process in every case. So say if I find out, say this is the differential element of charge, it will create an electric field over there in that direction. By the same analogy, there will be one more electric field from that part, it will be towards opposite direction. So they will cancel out from this part, we'll find out only that vertically upward part. So that's mean to find out that electric field for the whole rate, I'm going to integrate that part. So that should be, integrate is nothing, basically the sum up, right? Say I have that part and there will be infinite number of small segment. So that I have to add them together to find out the net electric field for this rod. So that's mean I can write down the electric field by this line of charge would be basically infinite, say contribution of the electric field of differential element. So this is actually summation sign, right? The summation sign we can use basically that extended, which would be actually the integrate. So I'm going to integrate this one from minus L by 2 to the plus L by 2. I choose the origin at the middle actually. So that's why I write down minus L by 2 to the plus L by 2, say by a differential element. Fine. So this will be my procedure to find out that electric field, total electric field for this continuous distribution charge. We'll follow the same procedure for any other shape of object. Fine. Say if I choose that element, or I can write, say there's say differential element, say that element is create a electric field, say D instead of that one. So since I'm going to integrate D differential element, will be create the K dq over R square, right? This will be magnitude. To find out that vector, since electric field is a vector, I will write down the R hat, right? Then the total electric field. So this is actually the electric field for, say that contribution by a differential element. In the figure, we can also say that. So I choose, this is the differential element. And for this differential element, I'm going to find out the electric field over there. So this will be the case. And this is actually my R vector, R head. R head will be towards that direction. Fine. For the total electric field, then what I have to do, I have to do that integrate minus L by 2 to plus L by 2 into D, right? Then I'm going to put that value of this dE. It will be minus L by 2 to plus L by 2 K into dQ over R square into R head. Now what is R head? R head basically the unit vector in the direction of that vector. Right? This will be the R head. So to find out that R head, I'm going to write down, it should be that since I'll take that component basically, say it will create an angle from there, is the create the angle over there, that angle we can also find out, say this one is with the same, right? If we sorry, that not that one, I'm sorry, it's with 90 degree. So if you consider, so this is a line, then that angle and that angle is going to be the same, and you can find out the component of that vector, which is R head. One vector would be, say, I'm going to write, use a different color. One vector would be towards that direction, another vector would be towards that direction. Right, am I right? Or I can say that angle is not over here. I choose the angle. It would be difficult to understand if we draw the angle over here. It's depend on where the angle is created, right? I hope you can do that one. Say this is the vector R head. Say that create the angle over here. Say that this angle is basically θ1. In that case, you'll find out the component of this vector would be, one vector will be towards that direction, another vector will be towards that direction, right? I could find out this R head using that component method. I could write this R head would be minus K sine theta, or θ1, sorry, I write on the θ1, because look at this. This will be one component toward this direction, because create the angle over here with the x-axis, then the z-axis it would be that sine component. But it's, since it's the origin over here, it is toward the negative z-axis. So that's why I write down the minus K sine theta, so K head plus I head cos theta. Right, and we can say that that R would be also root over x square plus z square. Now we can find out that cos theta in that case, using the trigonometric definition, will be x by R. It will be, you can find out. So it's not a cos theta, sorry, it's a cos theta 1, because I use the notation for theta 1 over there. Then in that case, it's going to be basically x by R is x square plus z square, right? I hope you can understand, say. And this is the case. This is my triangle. This is the create the angle over here. This is actually your R, right? So this angle is 90 degree. In that case, the cos theta, this is the x component, and this is actually that z component. So cos theta 1 would be base over hypotenuse. Base is x, and hypotenuse is actually the R. So that's how we can find out this ratio. Also the sine theta we can also find out in a diaphragm. Now this, by the analogy with this, you will find out one more case, and this one will be also the same over here, but it will be towards that direction, so they will cancel out each other. So I'll find out only that cosine component over there. They will cancel out basically that x component, or the sine theta will be basically they cancel out from there, because one component, if you think about, for say I'm using different color, say at the same time this is actually one component will be towards that direction and another component will be towards that direction. So that means this component and that component with the opposite direction, they will cancel out each other. So we'll find out only that x component. So that's why you can write that total electric field in that case would be electric field L at point P into I hat. So this is a BEL, electric field for the line charge. I can write it will be minus L by 2 to plus L by 2, which is K dq over R square. R is basically x square plus z square into R hat. So R hat, I write down vector by vector magnitude, which will be cancelled out. In that case, I'll find out only this is will be the cos theta component, because sine theta component will be cancel out each other. Fine. So now we can do some calculation over here. So what would be there? I can write down. So this is would be minus L by 2 to plus L by 2 k into dq. dq I can write lambda into dz. Basically, we define the linear charge density lambda into dq over dz equal to total q divided by total charge, right? So this is called the linear charge density. I replace that dq by that dz is lambda into dz divided by x square plus z square into cos theta. We define that part actually x into root over z square plus x square. Now you can jump over here, basically this EL, electric field for the line charge, I hat minus L by 2, that part basically the mathematics. So k lambda into dz divided by x square plus y square root over 3 by 2. Now this lambda k is constant, right? So it's not a y square, I'm sorry, it's a z square. I make a mistake, I write down the y. It's z square. This one I'll factor out. So this EL would be I hat k. There is also the x. I forget to write down this x. This x is also the fixed, because we find out x at a distance, right? Which is actually that 4 meter over here. This is the x direction. So this way it is fixed. You can say this is the constant. I can factor out this one kx into lambda is a minus L by 2 to plus L by 2 into dz divided by x square plus z square 3 by 2. Now this is actually that a formula we can use from the integration. There is a definite integration formula, so you can use, we know that. So if a function dx over x square plus a square 3 by 2, then this answer would be a into x over a square x square upon a square. So this is actually the standard formula of this integration of this thing actually. Using that formula for our case, we can write down this answer would be E would be I hat k lambda into x. It would be z divided by x square into z square plus x square, and this would be minus L by 2 to plus L by 2. Right, now x is constant, only variable is the z, right? I can factor out this x square from there. If I do that, I'll find out I hat k lambda divided by x, because one x will be cancelled out. Then I'll find, I'm to put that value of this z, because j is variable over here, right? L by 2 divided by L by 4 plus x square plus, because if you put the minus limit over here, I had to write down at a time, plus L square by 4 plus x square. I just put the value of the limit. In that case, I'll find out this electric field would be I into k into lambda divided by x into L divided by L square by 4 plus x square. This is actually the general formula. This is, don't try to memorize this formula. Actually, you cannot do that. You have to derive in that form. So this is actually my electric field for this line of charge. Now I have to also modify this equation. Why? Because he say that it's a infinite long. So infinite long means I can say L is much greater than x, right? This line of charge is infinitely long. So that means it's going to that direction. If it is that, with respect to that length, we can neglect that distance, which is actually the x over there. So if the case is that into that equation L is much greater than x, what we can modify? We can modify, look at this, I have to modify this equation. So I will write say k by lambda in divided by x, and this one L I can factor out from L square by 4 into that equation. I'll find out 1 plus 4x square by L square, right? Then EL would be I k lambda by x. This one would be basically L by 2 is going to be 1 plus 4x square by L square. Since L is much greater than x, so this term we can neglect because it would be closely to 0, right? 4x square divided by L square, because L is much higher than x. So that's why we can write this EL would be I k lambda x. This L will be cancelled out. I'll find out 2. That should be that 1, right? Then we can say that this electric field for this line of charge is going to be twice k lambda divided by x into I hat. This is will be that electric field for line charge for this case. And this is, remember, this is basically the discretional case. But the general case, the general formula is this one for it, and it long charts of we can find out in that form. So fine. Now I know the K, which is Coulomb constant, and I know that linear charge density, and I also know the X. So if I do that, I'll find out this L would be 2 into 9 into 10 to the power 9, and linear charge density is 0.6 into 10 to the power minus 6 divided by X is 4 meter, right? So I had, and I'll find out this EL would be 2.7 into 10 to the power 3 Newton Coulomb. This is the electric field for the rod at the point P. Fine. Now I have to find out the electric field for point charge. For the point charge, now for point charge, we'll write the electric field by this equation. Electric field for the point charge, K Q over R square into R hat, right? Now, or you can write down this is a RP so that you can differentiate. The RP is now that unit vector for this point charge. This is the RP, which will be toward that direction, right? This is that unit vector for RP. It has two components. One is towards the positive X direction, and another would be towards that negative Y direction. Since it's create the angle, the theta over there, and this angle would be also that theta, right? In this unit vector RP head, I can write this RP head would be basically that cos theta I head minus sin theta Z head, right? Where RP magnitude would be basically 3 square plus 4 square, that's going to 5, because you can find out. So this one, your P point, this is the P point, and this is the charge, which is actually the 3, and this one actually X, actually the 4. Look at this in the diagram. This distance from here to here, from that point to that point, is the 4 meter is given, and that distance actually the 3 meter is given. This will be the right angle triangle right over here. So that's why this magnitude of that one would be basically that 5 RP magnitude. Fine. Now I can write down this EP. So this EP is going to be that 9 into 10 to the 9. Charge is 8 microcoulomb, 8 into 10 to the minus 6 divided by RP magnitude of 5 square into RP head. This will be cos theta I head minus sin theta Z head, right? And this one is cos theta I can write because I have to find out that one. So this cos theta would be, because that one we define that theta over here. This one actually that EO theta. Then cos theta would be 4 by 5 because that hypotenuse is 5, and sin theta would be 3 by 5. From that figure we can find out. And we'll put this information over here and write down EP. Say basically, if you calculate this one, you'll find out 288 into 4/5 I head minus 3/5 Z head. If you do that calculation, you'll find out it will be 2.3 into 10 to the 3 I head minus 1.73 into 10 to the 3 Z head. This is for the contribution for the point charge at point P. Fine. Now I'm going to find out the resultant. So sum of that actually. So E net would be electric field for the line charge plus the electric field by the point charge. So this is actually electric field by the point charge, and we also find out the electric field by that line charge. And if you add, we'll find out, you're going to add them together, you'll find out E net would be 5 into 10 to the 3 I head minus 1.73 into 10 to the 3 Z head. This is actually that answer. And I hope you can find out the magnitude and the direction of this vector. So they're asking me to calculate this one. So this is actually that contribution of the point charge and the line charge at the same time. So that's how we can deal with this thing in that way. Okay, fine. So do you have any question on that, whatever I talked today? Hello?
No, sir.
Okay, fine. If you don't have any question, you can leave. So this is actually the end of the second week. Have a nice weekend. We'll meet again in the next week. So before that, be safe and stay at your home. Thank you very much.